I feel as though today would be a good day to just go through a review here, a brief review from the beginning. We're getting close to the end of the unit. The final two topics, which are covered over 4 days, will be covered today, tomorrow, Friday, and Monday, and then Tuesday and Wednesday of next week will be our planned review days, and Thursday of next week will be your first unit exam. So even though we only have really 2 topics left, the topics can be pretty deep. So this is just an opportunity to review everything from the beginning before we go on. So to begin with, we started off knowing that momentum is mass times velocity. I feel as though I probably shouldn't have to even say that it's obvious. It's also evident because it's a formula that appears on your formula sheet, but I want to take the opportunity to remind you that momentum is a vector, and that means direction needs to be included. Unless you're interested only in the magnitude of the momentum, in which case we don't have to worry about direction in our answer. But I should have mentioned, in many problems, if you don't include direction, you're not going to get the right answer. What that means for you as a student is you won't get the marks. What that means as a physicist is you would predict incorrect things. Your lander is going to crash on Mars instead of landing safely, things like that. Scalars are things that have magnitude only, and the examples I've given you in class include mass, energy, charge, and time. Energy, again, is that one that you tend to want to say it's a vector. And I don't know why, but people do. So I've included in the list explicitly. Vectors are things that have magnitude and direction. I've got momentum, impulse, velocity, force, acceleration. As I review this stuff again and again and again, what you're going to discover is I kind of amp things up a bit. I've never mentioned electric field or magnetic field. You should know a gravitational field has a direction. So now I'm just kind of, dipping our toe in the water to get a feel for what it's like out there in terms of other things. These are fields that have direction. Impulse is defined as a change in an object's momentum, so now we're getting close to what we did a couple of days ago. It can be found using m delta v or f delta t. The reason it can be found using f delta t is because we derived this formula in class relating the net average force acting on an object to its mass, its change in velocity, and the time over which that force is applied. When you use that formula, or when you calculate impulse using f delta t and m delta v, anytime there's a vector, direction is important. It's not that somebody said, let's just put a bow on all these things and put an arrow over top because it looks nice. It has a purpose. And you need to pay attention to whether something is a vector or not. I shouldn't need to say to you, but I will. Delta v means final velocity minus initial velocity. Final minus initial. And you need to include directions. It's velocity. I've never been a fan in physics of talking about delta t, which means t2 minus t1. It's t. It's time. How many seconds have elapsed? We also talked about, and this comes out of the equation that's highlighted here, we also talked about safety devices. If I go back to this equation, if you have a 50-kilogram person moving at 20 meters per second, and that person is going to be stopped. How? Doesn't matter. That person is going to be stopped. If you take their 50 times, if they're moving at 20 meters per second and are going to stop, 20 meters per second is essentially their change in velocity. It will be negative 20, but I don't care. If you multiply those two quantities together, you get 1,000 units of momentum that they have. And if they're going to stop, they're going to end up with 0 units of momentum. So regardless of how they stop, their impulse will be negative 1,000 units of momentum. How's my multiplication? 50 times 20, 1,000. Regardless of how they stop, this product has to be, in my example, negative 1,000 units of momentum. And it's negative because it's final momentum minus initial momentum. So how can we produce that impulse? We do it by applying a force over a time. If the time is very tiny, the force necessarily has to be large. If you want a smaller force, then the time has to be more. This is the idea behind a safety device, an airbag. Let's choose a different example. When I drop an egg onto the floor, it's going to break if it hits the floor, but if I put a pillow there and it hits the pillow stopping the egg, its likelihood of breaking is not as great. It still might break, right? Depending on the height. But it might not. And the reason is not because the pillow is soft. That's the reason if you're in grade 5. Okay? In physics 30, the reason is the pillow starts applying a force to the egg at one point, and then it draws out the time that that force is applied, finally stopping it. So it increases the distance and it increases the time. If it increases the time, it doesn't need as much force. Okay? I mean, there are some other things I said here. I shouldn't just brush this away. This statement here is really important. You know, if you see a question on an exam that talks about the reason why the car that hits the safety barrier, or it compares a car that hits a safety barrier to a car that hits a concrete wall, and you're asked to compare them, I guarantee you, 9 times out of 10, one of the choices will be that the car that hits the concrete barrier experiences a larger impulse. And boy, that's a tasty little morsel to grab onto. It seems reasonable, right? But it's wrong. Both cars would experience the same impulse. The difference is the car that hits the concrete barrier experiences a greater force in a smaller time, producing the same impulse. Now, yesterday we learned that area of force graphs tells us something. The area associated with a force time graph tells you the impulse. The area associated with a force displacement time tells you the displacement. And to kind of just put a cherry on top of all of this area stuff, if you have part of the graph that's below the time axis, then that area is mathematically considered a negative, and that impulse is negative. I hope you understand why the impulse is negative, because we're dealing with negative forces. And the last thing I've got here is, you know, putting this all together with area from yesterday. If area of a force time graph is impulse, and I presented this to you yesterday but in a different visual, and F delta T is impulse, and M delta V is impulse, then all three of those things are equal to everything else. Each of them is equal to the other two. So you can write F delta T equals M delta V. You can write F delta T equals area. You can write area equals M delta V.